Good morning, class. This is Eric Patterson. I'm recording lecture from a hotel room in Seattle, Washington. And this is a makeup lecture for last Friday where we were talking about hole resistance and other drag components. So the objectives of this module is threefold. One is to understand that resistance is fundamentally due to surface pressure and wall shear stress on all surfaces of the vessel that are in the water and air. We've talked about that a little bit, and in the last week or so we've talked about integrating surface pressure and wall skin friction to get these components of resistance. Number two is that we want to understand that the total resistance can be split into components, each of which can be modeled using empirical data and relationships. And three, we want to understand and appreciate that dimensional analysis is critically important for extrapolating model scale data to the ship prototype. So here's a chart that shows that at the very top is the total resistance, C sub T. And at the top level, we can split that into the pressure resistance, C sub P, and the skin friction resistance, C sub F. The total pressure has these two components, and the pressure resistance is always due to the normal force, and the skin friction is due to the tangential force. So if we were to look on the surface of the hull down here on the left, we would have the pressure acting normal to the hull, and then somewhere along the body we would have tau wall. Okay, skin friction coefficient, remember, is the integral of tau wall, and the pressure force is the integral of the pressure. The skin friction is easy to understand in context of a two-dimensional flat plate. Okay, and typically this comes from the ITTC friction line, which says that C sub F0 is equal to 0.05 all over the logarithm base 10 of the Reynolds number minus 2 quantity squared. Let's see if we can get that there. Quantity squared. That empirical correlation came from years of testing flat plates and towing tanks around the world, and now it's a pretty well accepted standard. The pressure also feeds into three-dimensional effects as some correction, delta sub CF. You can see it here. We'll talk about that over time, but that's a three-dimensional effect. Together, these two give you the pressure resistance, okay, the primary component of the pressure resistance. However, there is a third part here called the viscous pressure drag, right here, C sub V sub P, and that feeds down into what sometimes is called the total viscous energy lost in the wake, C sub V. And you can see there's transom drag. There's some component of transom drag due to recirculation, almost like if you had in this region on the ship on the left, you can see it doesn't really show a big separated region. It shows the streamlines coming in smoothly. But you could imagine if you had a surface combatant, you might get some separated flow here. This would be separated flow that would lead to transom drag. Now the pressure force on the left-hand side of the diagram, the pressure force really leads into the wave pattern, wave breaking and spray, which, interestingly, anything that is viscous, like wave breaking, energy loss, feeds over into the viscous part. But it has a pressure or a wave resistance part that feeds straight down into the total wave resistance. There is an induced drag due to lift on the hull, just like when we're talking about airplanes. Whenever you generate lift, you generate induced drag. So for high-speed ships that are lifting bodies, you'll generate induced drag. Ultimately, though, we have two primary components that can be recast, from pressure and skin friction at the top to wave resistance at the bottom here, total wave resistance C sub W, and total viscous C sub V. This is energy lost in the wake, and the wave resistance is the energy lost in the wave. In the waves that are propagated away from the ship over here on the left, all of these wave fronts, okay, and then usually you'll get some sort of transverse wave pattern in the wake. All of that energy radiates away from the ship. And so we have to account for both modes. So this just is a recapitulation of the fact that the pressure field around the ship creates waves. Usually we have high pressure at the bow and then pressure recovery at the stern. Mid-body, there'll be a low pressure. The flow is accelerated. That's why it's plus V. The flow is accelerated. Pressure, therefore, drops. All of that's per the Bernoulli equation. And it results in a system of waves known as the Kelvin wave pattern. You can see it here on the bottom, the Kelvin wave pattern. Goes back over 100 years that we first were able to identify the Kelvin wave pattern. And you can see here the transverse waves that I mentioned a minute ago. There's the transverse wave pattern. And the diverging wave pattern, right, is on the sides here. Those are the diverging waves. And for slow ships, there's some critical Froude number we'll see in a second, but for slow ships, usually the diverging wave pattern, it can be proven mathematically that the diverging angle is 19.47 degrees, right here, and that the wavelength is completely a function of just the ship speed. Okay, so it's 2 pi times v squared over g. Okay, so that's the wavelength of the transverse waves have a wavelength equal to 2 pi v squared over g. So you know, based on the ship speed, what that wavelength is. Okay? And the overall wave field is comprised of various sources. Okay? And usually you'll have a bow wave. Over here on the right, you'll see you'll have a bow wave. You'll have a stern wave that's created by the pressure field at the bow and stern. And then depending on the geometry of the ship, you might have a forward shoulder wave and an aft shoulder wave. And we need to add these wave patterns up to get the composite. Okay, so these all feed into the overall composite wave pattern. Composite overall wave pattern. Now we can predict this with CFD, luckily, in the modern with modern CFD codes like the one you're learning to use. 20 years ago, we would, and even today for fast simulations, people will use potential flow codes where you distribute singularities on the body and solve a boundary element problem. Well, it's interesting. If we look at low-speed bodies on the surface, even ducks generate diverging wave pattern. And so the question would be, what is the duck's typical Froude number, right? Froude number is defined as their swimming speed over GL. Anybody be able to guess what the duck's resistance is? Well, it's much less than 1, that's for sure. We'll come back to this in a second. Is the diverging wave, as known as the Kelvin wave, is it at the same angle as for a displacement hull ship? The answer is yes. Okay, that's that 19 degrees. So this wave angle for each of the ducks, that's kind of all mixed together because they're all merging together. And the answer to this is it universal? for all speeds? No, it's not universal for all speeds. It's for displacement hulls, yes, especially for displacement hulls below some speed, known as the hull speed. It's universal, but for higher speed ships, it most definitely is not universal. So here's a chart that shows this. So below some speed, the wake angle, that's what this is on this axis here, is the 19.5 degrees. And then above some critical Froude number, the wake narrows substantially. Okay, so this region here is very similar to what we see in the Mach cone for supersonic flight. Right? So what happens is we end up, for this high-speed ship here, right, we end up with an angle that's very much narrower than 19.5 degrees. In normal naval architecture, we refer to the humps and hollows of wave drag. Okay, so on this, you can see this region here, this would be a hollow. So this chart is the ship resistance versus speed. Okay, and we see regions that are hollows and then humps. Okay, so this is the terminology that you'll sometimes see. Hollows are here, okay? And it's because of the fact that as the ship speed increases, the wavelength changes. And as the wavelength changes, you get superposition of the lengths of individual waves, and the resistance will actually change from maybe what you might anticipate, and you'll get these humps and hollows. So you could imagine, right? You might want to choose to operate in a hollow. You might choose to operate in a hollow versus, a little increase in speed results in a very large increase in resistance. Okay? So again, we can kind of get an estimate. We can get an estimate of the wavelength based on ship speed. So typically, the hollows occur. When do they occur? When the bow crests coincide with the stern troughs, and the humps occur when the bow crests coincide with the stern crest. It's a superposition of the waves, and you get an increase in drag. Okay, so here's a table that shows at what speeds and Froude numbers the humps and hollows occur. And it has to do, again, with the superposition of the waves. Let's move on to appendage drag. Appendages are critical for being able to maneuver. So, right, we use rudders to maneuver. This picture on the top left here. Right, rudders help maneuver the ship. Stabilizers stabilize the ship. They help reduce roll. So do the bilge keels, like down here on the bottom. Bilge keels help keep the ship from rolling in high sea state. Propeller bossing, like this, you can see here on the top right. Shaft brackets, this region here, this whole bracket, the whole purpose of it is to hold the propeller shaft, but it still causes drag. And then in the middle bottom picture here, that's a picture of the DDG-51, the Arleigh Burke class destroyer. You can see that there are very big propeller shafts. So we got the propeller shaft, the struts. Okay, these cause a lot of an increase in the surface area, and therefore an increase in the attendant drag. So appendage drag can be up to 25% of the bare hull resistance. We have to take a lot of care in designing the appendages. Now, hopefully, you've done a good job in designing your ship. So with careful alignment, the resistance of the appendages will mostly be from the skin friction. And that means it can be based upon the wetted surface area right here. S, remember S is wetted surface area. And wetted surface area, and S sub APP is wetted surface area of the appendages. So we can write out, based on the definition of the skin friction coefficient, right, R sub F over 1/2 rho S V squared. We can calculate the RF if we know what it all comes down to. Do we know what CF is? So if we know if we know the wetted surface area, we could get this from the ITTC friction line, which is only a function of speed, really the Reynolds number. However, if you've not done a good job designing your ship, meaning if you have poor alignment, you can get flow separation, unwanted lift, induced drag. You could have an appendage near the free surface and it could create wave drag. And there might be situations where you have a velocity gradient over the appendage, and therefore this velocity is not constant. Okay, so that's what this means here. If the velocity is not constant, you can have a problem in computing R sub F. But hopefully you've done a good job, and the appendages are aligned with the flow. Now, an example though of velocity gradients. Let's imagine we're looking at the model. So this is maybe a 6-meter model. It's about 20 feet long. You're testing it up at the Navy lab in the big towing tank. In that case, the boundary layer is thick, relatively speaking, right? So the boundary layer, incoming boundary layer, is here. Okay, and then on the ship, which let's say the ship is 200 meters. Let's assume it's a 600-foot long ship, roughly 600 or 200 meters. Now, relatively speaking, the boundary layer is very thin. So this part of the rudder is out in the free stream. Okay, very different. These are very different situations. Okay, very different situations. You have to take that into account. So you have to know what the velocity gradients, if there are any, across your appendages. To estimate appendage drag, you can do a couple different ways. One is you can test the model with and without appendages, and this is often called the stripping test. Stripping test. You know, you add the appendages on one at a time. Another way is the form factor approach. Okay, you have some form factor. The form factor is 1 plus k. Okay, that's what 1 plus k is called the form factor. And so if you know the drag coefficient for the model, this is for the model, you can estimate the drag coefficient for the ship. And that's the whole process of extrapolation. We'll talk about that in one of the next lectures. Another way to estimate appendage drag is you can test isolated appendages, for example, rudders in a wind or water tunnel, and try to get full-scale drag. And then finally, what's often done is use empirical data and curve fit equations from experience, from earlier model and full-scale tests. Another famous book, and I've put this book on the Canvas site, is the book by Horner. Okay, Horner's book has extensive data in it. The reason I've put it out there is because it's out of print, and I've put the PDF on Canvas for you. It's a great compendium of data. I highly recommend that you take a look at it. Whenever we talk about components of resistance, we also have to worry about air resistance. Okay, air resistance of hull and the superstructure. So on the left is a big tanker. You can imagine there's a lot of air resistance or drag from that superstructure and all the containers. And for the Navy ship on the right, there's a lot of projected area. So the key to all of this, the key idea is what's the projected area? Projected area is going to create a lot of resistance. Okay, so here, if you want to estimate the area, the resistance due to hull and superstructure, again, it's fundamentally based upon the definition of the drag coefficient, right? 1/2 rho, the drag coefficient's 1/2 rho of the air, because we're talking about resistance in the air, the projected area, A sub p, and the velocity, the relative wind, or velocity of the air over the ship. So I can solve for R sub A as long as I know what the drag coefficient is. And that's the value of the Horner's book. Okay, so for example, we get all of these drag coefficients from Horner. You go in and you find, oh, I can model, I got a ship, and I got some superstructure here. What is the shape? What's the drag coefficient of this? You can model it as a square plate or a square box or whatever. Get the drag coefficient, put it in your formula here, and get an estimate for the resistance. Some of the primary issues that you have to be aware of, number one is shielding. So downstream, you might have a downstream superstructure that has to be accounted for. Another example, you have a really tall bow. Flow comes up over the bow, and this is all recirculating region here. You have to take that into account. Another one is the velocity gradients, and we've mentioned that in context of the difference between model and full scale. But here's a case where you have atmospheric boundary, or let's call it, instead of atmospheric boundary layers, be more precise and call it the marine boundary layer. And this is in still air, and this might be in a headwind. All right, so in one case you have uniform flow, and in another case you have a gradient called the boundary layer, right? So you got to take that into account. And how would you do it? Well, you might say, well, at this elevation I have that speed, and at this elevation I have a different speed. Okay, you'd have a lower speed at different parts, and you would use maybe the idea of strip theory. Strip theory, where you model each shape of the hull or the superstructure in a series of strips and then add them up or integrate in the vertical direction. Another very important concept in resistance is the idea of roughness and fouling. The marine environment is brutal, and what that means is that we get roughness due to fouling and surface effects. Fouling includes slime, weed, and animal materials, and surface effects include, coatings, corrosion, cracking, something called cold flow of coating, okay, where the coating fails. All of these things can affect the resistance, especially over the life of the ship. Okay, these are usually things that happen over time. So when you do the sea trials, when the ship is built, you'll have very different resistance than you would maybe several years later. Okay, there are specific areas of the ship that are often susceptible to biofouling, right? So if you have locally high shear, it's like in the middle of the hull, right? You have good shear because you have good flow over it. You'll have low fouling. But in some regions, right, you can see some typical areas, anchor locker, bow thrusters, that don't get turned on very often. Something called the sea chest, where you exchange water from in and outside the ship, the keel, external cooling pipes, maybe in regions around the propeller, not on the propeller blades themselves usually, but maybe in junctures where you don't get good washing, you'll get high fouling. That can be a problem. Okay, this comes back to the point I was making. So what happens typically is the fouling will increase over time. The roughness then goes up, and you'll get some increase, some delta CT. You'll get some growth, and then you'll bring it in to the shipyard and do periodic dock. In this case, I guess you'll bring it into the dry dock, clean off the ship, and repaint it. And then you go back out for another couple years, and the resistance increases. Okay? And maybe they'll come in and shot blast the hull, sand blast or shot blast it, clean everything off, repaint it, and again, though, that only has a finite life. And so you have to account for the growth of roughness and fouling over time. It gets more rough, and associated with it, you get an increase in resistance. The way we understand roughness as engineers is we relate it to a friction line. Okay, so some friction versus Reynolds number. And we know that if it's hydraulically smooth turbulent line, this is sometimes called hydraulically smooth. Hydraulically smooth, or harkens back to the days when we tested all of these different materials in pipes. We would coat the inside of a pipe with different materials and measure the flow rate and the pressure drop, and we could understand the effective roughness on the resistance. And what we see is, as we increase roughness, there's a couple things that we know. One is the roughness. With an increase in roughness, right, we get an increase in resistance, C sub F. And we also see that for higher roughness, it becomes uniform for larger, the resistance becomes uniform for larger expanses of Reynolds number. Okay? So much larger range of Reynolds number, because it becomes fully rough, is what it's called. Ultimately, though, we want to be able to predict this. So if we know the size of the barnacles, if we know that your ship is encrusted with barnacles, we know that we have an effective grain size, right? We can calculate the resistance from this empirical equation. Okay, so K sub S is 5,000 for barnacles. You think about how that compares to plate glass, something highly polished. Right? Plate glass is here. We're talking about an increase of what? 50,000. 50,000 increase. 4 orders of magnitude, 10 to the 4th increase in this coefficient. So resistance can go up enormously with increased roughness. We also know that resistance goes up with wind and waves, okay? So the power requirement in rough weather increases significantly. Rough weather increases the resistance significantly. Also in rough weather, operators usually slow down, right? Because if the bow is slamming into the waves, usually it'll slow down. And at the design stage, we want to be able to estimate power increases due to rough wind and waves, particularly at full speed. Okay, so we need to know something about the climate that the ship is going to be operated in and where it's going to be. What's the route? Okay, so we have to know that so that we can estimate the increases in resistance, and you have to look at historical data. And typically we rely upon experimental and theoretical methods to estimate the influence of wind and waves on the ship speed and power. Okay, I recommend that you read section 324. You've already been assigned the entire chapter, so I expect that you've read this chapter and this section already. Now, we want to refer to something we call this power margin or service power margin. Typically, you'll start out the analysis. Basic ship power estimates will be for clean hull and the propeller in calm water. Okay, that's going to be the basis. Clean hull and propeller in calm water. However, over life, as we talked about a minute ago, the hull will roughen and foul, and the ship will encounter wind and waves. Both lead to an increase in resistance, so we must include a margin, okay, to account for these. Sometimes we just take a flat margin of 25% if we don't have good estimates of where the ship will operate or how the roughness will increase over life. Okay? So that ends today's lecture. We'll next shift gears to computational fluid dynamics, a little overview of that. Have a good day, and I'll see you guys back in class soon.